In this video, we will start the second section of high-performance programming for HEAP course. The title of this section is Parallel Programming. In the first video of section 2, we will introduce some basic parallel programming concepts, including processes, threads, and context. What are processes, threads, and context? How can we manage processes, threads, and context in parallel programming? First, let's review the relationship between these concepts. Typically, as programmers, we develop applications. An application can be either a web browser or a large-scale physics simulation. Any application can be divided into one or more processes. Then, each process can be further divided into one or more threads. So, applications, processes, and threads can generally be organized in a tree structure. Of course, this is a little bit oversimplified. Your CPUs and operating systems have complex implementations to manage the processes and threads. But as software application developer, understanding the tree structure of applications, processes, and threads is sufficient. As you may have realized, we have not talked about context here. So what is a context? In a Linux system, a context can be generally considered equivalent to threads. Context is a terminology for the operating system and the GPU hardware, while threads is a terminology used by programmers when developing the software. Now, since we know the relationships between the key concepts, let's look at how to use them. Let's start by talking a little bit about processes. How to create a process. If you use C or C++, you can use the fork function. The fork function will copy the current process to create a new process. In the parent process, the fork function will return the process ID of the process that is just created. Since we mentioned the process ID, or PID for short, we want to discuss why it matters so much. The PID is critical because it identifies a virtual address space. In a program, when we have a pointer, it stores the address to a memory location. The address is a virtual address. To access data in the memory hardware, we need to translate the address to a physical address. Your operating system or your CPU will need to manage an address table. An address table can be abstracted as a table with at least 3 columns: the PID, the virtual address, and the physical address. Your operating system will need to use the PID and the virtual address as the index to look up the physical address. While the virtual address to the physical address adds performance overhead, it enables a more flexible address space management scheme. Your application can use the whole address space regardless of where your data is actually located. Here, we have an example of a page table with 2 entries. These 2 entries both have a virtual address of 10000, but they are mapped to different physical addresses. Suppose process 1 has 2 threads and process 2 has 1 thread. Then the 2 threads in process 1 translate address 10000. They will both get physical address of 40000. And both these 2 threads can read and write the same piece of data. However, if the thread in process 2 translates address 10000, it will get a physical address of 60000. This data at physical address 60000 is not the same data in physical address 40000. This example shows the threads in the same process can share data while threads in different processes cannot easily share data. Sharing memory is both a good thing and a bad thing. It depends on what you need. For example, if you're writing a web browser and you have 2 browser types running, you don't want these 2 websites to communicate because you don't want one website to see the password you typed in the other website. In this case, you probably want to separate these browser tabs into 2 processes. But for most high-performance computing applications, the application will only run your own code. And you should trust your own code. So it is not a security issue, and you want to share memory easily most of the time. Therefore, using threads will be a better option. Okay, next, let's talk a little bit more about threads. How to create a thread. There are many different ways. First, we have the pthread API. If you are writing a pure C program, you probably want to use the pthread APIs. If you are using C++, C++ has its own thread APIs, which are slightly easier and more user-friendly than pthread API. It is also very popular in the high-performance computing domain to use MPI to manage many threads. MPI will take care of the thread creating process and the data sharing process so that you can focus on the logic of your program. You can consider MPI as a wrapper of the pthread API, so the underlying mechanism still involves pthread. The next question is why we want to use threads rather than processes. First, threads can share memory. If we use threads, we don't need to copy memories across memory spaces. Inter-process communication can be a major performance overhead. Threads also have lower performance overhead for other reasons. For example, when creating a thread, we do not need to copy the state of the address space, which can save a lot of time and memory. Another reason is that context switching across processes involves replacing the address table, which may also increase latency. I hope this very brief introduction to the processes and threads clarifies their differences. Since this course focuses on high-performance computing applications, we focus on threads for the rest of the course. Since we're talking about context switching, we must understand context. As we discussed before, in a Linux system, a context can be generally considered as the thread. But from a CPU's perspective, your computer may be running many applications, and each application may have a large number of threads. The operating system includes a scheduler that picks a thread in the thread pool to be executed on one core. Remember, in the last lecture, we talked about that a CPU core can only run one thread at a time. Therefore, the thread scheduler must stop the currently running threads and start some idle threads so that all the applications can respond to user input and progress forward. This procedure that stops the running threads and starts running another thread is called context switching. The first step of context switching is storing the running context state back in the memory. Then, in the second step, the core fetches another context from memory and sets the registers correctly. The whole process is not latency free, hence we want to minimize the context switching as much as possible. Moreover, if the threads are from two different processes, the context switching procedure will also need switching the page table and may add extra latency. As we can see from the context switching procedure, context switching adds performance overhead, and we may not want to use too many threads. Later on, we will see how GPUs can avoid this problem and can easily manage thousands of threads to millions of threads.